So hi engineering Janta, I am back with another episode of our WTF series where we learn statistics for data science. So tell me in the chat section whether I am visible and audible to you people. If I am visible and audible, go ahead, type it out in the chat section. So tell me fast in the chat section whether I am visible and audible to you people. If I am visible and audible, you can go ahead and write out a yes, and then we'll begin with today's session. Great. Thank you guys. Great. So last time we had studied about correlations, and I'll revise it a bit and then we'll proceed further. We have studied a bit about correlations, and let me tell you, this is the second last episode of this series, and henceforth tomorrow will be the last episode of this series. Good evening everybody. So today we'll revise a bit about correlations because last week I was not very well and I was suffering from a few health ailments. Henceforth I was not in front of you guys. So I'll explain you a bit about correlations today. And as you all know that when we were discussing correlations, we had studied about Pearson's correlation coefficient, right? What was it? Covariance of x and y upon sigma. To track that actually how they are varying with each other, which particular distribution is more varied or which covariance is more stronger. We couldn't measure that. Henceforth, we needed something called as Pearson's correlation coefficient, or we needed correlation primarily because covariance couldn't do our job. Now, once we had this correlation, we found out that this particular type of correlation can help us in the linear distributions, where you can actually think that yes, this particular distribution is stronger positively correlated and other one is not so strongly positively correlated. Fine. So that way it was helping us. However, the issue with this kind of correlation coefficient is, number one, it is outlier sensitive. So if I introduce any very big value, this whole value distorts. Fine. This whole value gets damaged. So that is one problem. All those people who are not aware about outliers, all you need to do is you have to go and check about the outliers. You have to study about them. Fine. How do you study about them? How will you go ahead and learn these topics? I have already taught in the previous lectures. You can go ahead and watch them. Now, second problem was, it assumes that there is only linear relation between data variables. Fine. So variables, according to Pearson's correlation coefficient, it shows linear distribution of them. It considers they are linear in nature. ठीक है, ये मानता है कि linear है. अब इसके साथ problem क्या है? The point is that we can have some data. It assumes that data always varies like this, or it varies like this. Fine. However, this is not true. This is not at all true, because you'll have a lot of times when data would vary something like this. Data is increasing with every x. The value of y is increasing, but not in a linear manner. For some x, it is growing sharply. whereas for some x it is not growing so sharply. Fine. So for such distribution, Pearson's correlation coefficient never gets the job done. It never recommends you the correct things. Fine. It will never give you the correct result. It will never tell you how strongly the data points are varying. It will never tell you the correct measure. Fine. So in this case, what we can do? We have something called as Spearman's rank correlation coefficient. Fine. So you have something called as Spearman's rank correlation coefficient. Now what does this Spearman's rank correlation coefficient do? See, the formula for this is, often people term it as RS, or some people represent it with this small p. Fine. So I would go with this notation, R of S, and then covariance of rank of x comma rank of y upon standard deviation rank of x into standard deviation rank of y. So this particular formula is for Spearman's rank correlation coefficient. Fine. Now when this particular formula is for Spearman's rank correlation coefficient, let me tell you one thing. What is this R of x and R of y? We'll talk about it. This R of x, you can hold on your doubts, I'll come to them. Fine. So this R of x and R of y, these are ranks. For example, you have x, you have y. Fine. These are two variables. Fine. You have here 4, 5, 6 and 7. You have here 11, 19, 20 and 25. Now if you see, this is not a linear distribution. It is not increasing linearly. For 5 it grew exponentially, it grew very high. Then for 6 it didn't grow that much, right? Now in this case, what you can do is, we give rank to x and we give rank to the values of y. So the highest value here would be ranked highest, the lowest value would be ranked lowest. For example, 4 is the lowest value, so I give it rank 1. 5 is the highest, so 2, then 6, 3. Rather, we should change these values so that at least you get the proper hang of them. So I am changing them here. Fine. So I'll interchange their positions. That's all I'm doing. Fine. So here I'll name it this way. Fine. So 4 is lowest, 1, 5, 2, 6, 3, 7, 4. Now here in this case, what would happen? 25th is the highest value, 11 is the lowest, 1, fine, then 2, then 3 and then 4. In this manner they can be put. Fine. These are just ranks that I have given them. We can also give some ranks like this. For example, if you want to give some ranks, you can give it in a manner that they change, the positions of these values change. It can happen, let me tell you. However, once you assign the ranks, all you need to do is you calculate the covariance of these two variables. Fine. You do not look at them now. Now you calculate the covariance for these two. Fine. For this variable and this variable. These are ranks. Once you get the covariance, you divide it by the standard deviation of both. Individually you calculate standard deviation, you get your answer. This answer will always range between -1 to +1. Fine. More it is towards -1, it is negatively monotonic, more towards -1 is negatively monotonic, more towards +1 is positively monotonic. Fine. So why am I writing monotonic? Because it captures non-linear relationships as well. That is the reason. Now why it is important? Very simple answer. There is one concept in data science which is called as feature engineering. So in this feature engineering, there is another subsidiary concept called as feature selection. For example, when you're selecting features for a data set, say that you have a student whose performance you have to measure. Now, his study hours are a great metric to check for. His screen time is a great metric to check for. But there is one more thing. This screen time is actually negatively correlated to this marks, because more you increase the screen time, in general sense, consider that more you increase the screen time of any student, the lesser he would actually score in the exams, because he would not study. In this case, this is negatively correlated. Fine. And then you will have something called as, say, food choice. Now this food choice isn't that much effective in telling somebody's academic performance, right? So here, when you check about this food choice and when you check his performance, which is our target variable, fine. So when you check them, you will find they are not very strongly correlated. Spearman's rank correlation coefficient would give a very lesser value in terms of correlation, fine. Whereas you'll have a significant value here in terms of screen time, you'll have a significant value in terms of study hours, which will tell you that they are strongly correlated with it, which means they affect the performance. They affect the performance of a student. Henceforth, you need to be well versed with it. You need to know that these two features are important for me. And this is why Spearman's rank correlation coefficient is very, very important. Fine. By far, any doubts? If there are any doubts, go ahead, ask me out. And then I'll show you something very interesting on Wikipedia. Fine, go ahead. I'll show you a graph which is available there. So if there are any doubts, go ahead, tell me your doubts. If you have any doubts, go ahead, write them out. Fine. So I guess there is no doubt from your end. Fine. Good to go. Now let's go to Wikipedia and let's show you what actually you can go ahead and check out here. Fine. So I'll show you one interesting thing here. Where is it? Spearman's rank correlation coefficient. Fine. When you actually check it out on Wikipedia, you'll have a graph here. See, for this particular graph, fine, if you see, for every increasing value of x, y is actually increasing. In this particular area, whenever the value of x increases, the value of y is also increasing. However, when the value of x is ranging between 0.4 to 0.6, the value is not sharply increasing. But when it ranges from 0.8, or I would say 0.7, from 0.7 to 0.10, there is a sharp increase in the values of this particular type of distribution, isn't it? There is a sharp increase in the value of y for the values of x between 0.7 to 1.0. Pardon, I was saying 0.10. So this is not 0.10, this is 1.0. So 0.7 to 1.0, you have a sharp, steep increase, isn't it? Increase is happening throughout, but here you have a sharp increase. Fine. So this is not a linear distribution. It is clearly not a straight line. Henceforth, here, if you check for the Spearman's correlation, here the Spearman's correlation is 1, whereas Pearson's correlation is 0.88. Fine. The reason is, even if their relationship is not linear, it is monotonic in nature, but in the monotonic form also, it is increasing with the every value of x. Henceforth, the Spearman's correlation comes out to be 1. Fine. So this is the distribution that I wanted to show you, that monotonic distributions look like this, and that's why I had drawn a similar graph. So this is how monotonic relations look like. And the reason that this particular type of correlation is needed is when you have a value, for example, I'll draw this out. For example, when you have a value which is like this, say you have such value and suddenly you have a sharp increase here. Fine. So this value can be an outlier. If you carefully see, if I go by the ranks, say you have one value, let's give the values a different color. Fine. So you have one value here, second value, third value, fourth value, fifth value, sixth value, seventh value, and eighth value. Fine. Rather, I would not mention multiple values here. I would just say that you have a value which is here directly. Fine. An outlier. Now in this case, if I go by the Pearson's correlation coefficient, what does it say? Covariance of Pearson says correlation coefficient. This says covariance of x and y upon standard deviation of x and standard deviation of y. Fine, they are multiplied. Now, this particular outlier will change all these values very significantly. It would not give you a very accurate measure. Whereas, when I talk about Spearman's correlation coefficient, Spearman's rank correlation coefficient, for this would get rank 1, 2, 3, 4, 5 and 6. Despite being the outlier, it would get 6 as its rank. Same goes for the values of y. Fine. All the values of y here. Basically, I have given this value, this particular rank to all the x values here. Fine. All the x values here have these particular ranks. All the y values here will also have similar ranks. Fine. They'll also have similar ranks. 1, 2, 3, 4 and then what? Sorry, 4, 5 and 6. Similar ranks. Despite having an outlier, you'll have something which is rank which will not change very sharply. Henceforth, whatever measure you calculate would be not varying much and henceforth giving you a correct distribution. See, here it would become like covariance of R of x, which is rank of x, and rank of y upon standard deviation of rank of x into standard deviation of rank of y. So you can write it like this or you can write it like this, depends upon you, but this is one and the same thing. And what I want to tell you is, here ranks are being used. Henceforth, it would give you a better answer to the correlation of these two variables. Say this is y, say this is x. In this case, how x and y are correlated would be better given by the Spearman's rank correlation coefficient and not by the Pearson's correlation coefficient, because this is not a linear distribution, this is a monotonic distribution, and henceforth it is accordingly behaving. Fine. So I hope that clears the correlation part pretty much. As I told you, this is the second last class and in the next class we'll study the application of these descriptive statistics in the various domains of data science, and then we'll wrap this series up. Fine. So I hope this much is clear. If there are any doubts, go shoot them up. Otherwise, we'll wrap today's session. Okay, why we are wrapping this up? Okay, so the reason is that after this particular series, we'll run a poll that do you want the further classes on advanced statistics or do you want the classes on machine learning? Fine. So accordingly, we will start here. So that poll would be run very soon, and according to your response, we'll be going ahead with the classes. We'll be going ahead with the videos like this only. Daily we'll be going live and I'll be teaching you people. Fine. So go ahead. I hope that clears your doubt. So if it's clear, type out a yes. If it's not, type out a no. Great, great. So it's clear. So we'll wrap this session up, and with that, I'll say just one thing. Go ahead, keep on spreading knowledge as far as you can. Create an ecosystem of discourse in the society. Most welcome, Rashid. Most welcome, means you're going to teach us for sure either ML or stats. Now that's something you guys have to push me. Fine, and you have to tell in the comments of various videos. You should comment out below this video. You should go ahead in various polls if we post, and there you can go ahead and tell us. Fine. So with this, I'll tell you that create an ecosystem of discourse in the society. If you're studying from me, try your level best, and with that, keep doing good without any expectation for others. Good will come back to you in multiplied forms. I can promise you that. Have a wonderful day ahead. I'll take your leave. Bye bye.